All right, guys, how's everyone doing? Today's going to be a somewhat quick lesson, but make sure you have your calculators. We're going to be using our calculators again, right? It's a very calculator-intensive unit, but we are almost done for the year, and we have pretty much covered all of the topics we would have covered if we were in class together, right? But we are going to have to leave just a tiny bit out of the curriculum, unfortunately. So I will let you know what topics that we didn't cover if you and post some videos that you could watch if you're going to make those up. But we did pretty much finish, I would say, more than 95% of what we would have done in class, right? And to finish up next week, I want to have a quiz on Monday. All right, but before you get stressed out, just know that this quiz is optional. All right, this is going to be an optional quiz, and this quiz will only benefit you. And so if you haven't been doing too well this fourth quarter, please take the quiz seriously and try your best because it could help boost your grade up a bit. If you're happy with what you've done so far, please still take the quiz seriously. But just know that it's not going to hurt you if you do worse on it than your current fourth quarter average. So it's just a little freebie, but something everyone has a chance to do to give themselves a little boost. All right. So in the last two lessons, we've talked about linear regressions, right? So we have some data, something like this, right? And we said we could fit a line through it, right? And that line can kind of model the relationship between the two variables, whatever these two variables are, right? We looked at stuff like the weight of the car and fuel efficiency, the temperature, and the number of ice cream cones sold, right? But what if our data wasn't linear, right? Haven't we learned other kinds of functions this year, right? We learned about exponential functions, quadratic functions, absolute value functions, square root functions, right? So we're not going to be talking about all those different kinds of functions, just a couple of them. But just to remind ourselves of something we've done a while ago, let's try this warm up. All right, so go ahead and pause the video, see if you remember any of this. I'm pretty sure most of you will have completely forgotten about this, but let's take a look. All right, so the number of bacteria in a petri dish can be modeled using this equation, where y is the number of bacteria and x is the time in hours. What is the y-intercept? What does this represent? All right, so do you guys remember an equation where the x is the exponent, right? We call this an exponential function, right? So it's not linear, it's exponential. So what is the y-intercept of the equation? So if you forgot about exponential functions, well, we can still figure out the y-intercept because we know the y-intercept is when the x value is equal to 0. So if we're looking for the y-intercept here, all we got to do is plug in a 0 into this function, and we get y equals 100 times 1.4 to the 0 power. And hopefully you know that anything to the 0 power is equal to 1. Right? If you forgot that, you can type it straight into your calculator, and you will get 100. So the y-intercept is 100. Or more precisely, you can even write as a coordinate, 0, 100. So what does this represent? Well, that's our x, of course, and that's our y. And in the problem, it says that y is the number of bacteria, and x is the time in hours. So this is saying at time 0, we have 100 bacteria, right? Or the initial number of bacteria is 100, right? If you remembered exponential functions and you remembered something like this, y equals a times b to the x, right? Then you might remember that that a value is our y-intercept, right? And that b value, that is our growth or decay factor. So in this case, is this a growth or a decay? Well, that b value was 1.4. So if you remember, when we multiply by a number bigger than 1, it is growing, right? It is increasing. And then by what percent? Well, if you remember this form of our exponential growth, I think we used the t here, right? But remember, we looked at how much bigger it was than 1. So 1.4, it's bigger than 1, right? It's going to be a 40% growth, right? That 1.4, that's equal to 1 plus 0.4. And that is 40%. So it's a 40% growth each year. 40% growth. All right. So why the heck are we talking about exponential functions again? Well, like we mentioned before, we're doing other types of regressions, right? So not everything has to be a linear regression where we fit a line of best fit. We could do other kinds of best fit, right? What if our data looked like, well, I can't draw this too well. Well, actually, let's just look at the first example because that's exactly what it is. What if our data looked like this, right? So what we're doing here is we're going to determine if the best fit for the data is linear, exponential, or quadratic. So draw a curve of best fit depending on your choice. So a lot of you might look at this and say, all right, that looks pretty linear, right? And yeah, linear model might not be too bad, but I think a curved line, something like this, would be even better. And if you remember, that is what an exponential function looks like, right? So this would be an exponential function. And this is exponential growth, right? Because it's increasing. So I just put growth in parentheses. This should be a very familiar shape, I'm hoping, right? This was not too long ago. It was a while ago, but if I fit a curve of best fit, it might look something like this, right? And that is called a parabola. So this would be a quadratic function, right? The graph of the quadratic function is a parabola, right? Or U-shaped. It can be a smiley face or a frowny face. In this case, we know it's a negative quadratic. Aha. You might say this looks somewhat linear, but even better than linear, right? This could be an exponential function as well. This one is exponential decay, right? Because we're decreasing. So if our data looked like this, instead of doing a linear function, right, it would make more sense to do an exponential regression and fit an exponential function to our data, because an exponential curve fits the data better than a linear curve, right? Just like if you had data that looked like this, it would really not make sense to do a line of best fit, because how would you even draw the line? Would you draw it like this, or like that, right? So if the data looked like this, you would do a quadratic regression to fit the data, right? This one, that does look linear, so that would be a linear. This also looks pretty linear to me, right? And this last one, it's a U-shape, so that's going to be quadratic. So depending on what your data looks like, we can fit different kinds of curves to it, right? And the act of fitting a curve to data, or fitting a curve to make predictions or model the data, that's called performing a regression, right? So we're talking about other types of regressions today. So just like always, get out your calculator. Let's type this data in, and let's take a look at what this data looks like. So grab your calculators. Please do this with me. All right, so here we are. So to type in the data, right, we're going to add a lists and spreadsheet. Why do I have another page? Let me go brand new. Don't save anything. All right, lists and spreadsheet. So in this first example here, using a microscope, a researcher observed and recorded the number of bacteria spores on a piece of meat as it was heated to 400 degrees Fahrenheit over the course of 6 hours. The summary of the data she recorded is shown below. So at 0 hours, whoops, let me type this in first. So X represents hours, this represents the number of spores or the bacteria. I'm just going to type in bacteria. You can type in bacteria spores, whatever you want. So at 0 hours, we have 16380 bacteria. Right? After 2 hours, we have 1130. So it makes sense that the bacteria is going down, right? Because once you turn on the heat, bacteria is going to die. After 3 hours, we had 260. After 4 hours, there were 60 bacteria. After 5 hours, 15. After 6, 4, and we're quickly approaching 0. The bacteria is going to die out pretty soon. All of it, at least, right? So there's our data, right? And numbers, they should make sense, right? The bacteria is not going to be increasing if you are turning up the heat on them, right? So let's add a new page. And I want to visualize this data, so we're going to add a data and stats page. Right down here, this is our x value, so that's hours, our independent variable. And let's track the bacteria as time goes by. And there is our data. So using this data, write an exponential regression equation rounding all values to the nearest hundredth. So this definitely doesn't look linear, right? If I try to draw a straight line, I can draw a straight line like this that goes through most of the points, but then this point is way up there. So this definitely looks like an exponential, right? Just follow that mouse, right? That looks like an exponential decay curve. So if I go to menu, analyze, and then do regression, right? Instead of show linear, I'm going to go all the way down here to number 8 and do show exponential. Right? And you see how this exponential curve, wow, that fits the data really well, right? Whereas if I did this, don't actually do this yourselves, but if I did regression and I did show linear, right? This line, that is a pretty terrible job, right, at modeling the data. We wouldn't want to use this line to predict stuff, right? We want to use this exponential curve. So I'm going to delete that line. And this is the equation we want to use to model our data, right? This much more closely tracks the actual number of bacteria. So here we go. You could also do this the old way by using a calculator page, right? We can go to menu, what is it, stats, stat calculations, hold on one time, menu, stats, stat calculations, and instead of linear regression here, you would go down, 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 all the way down to choice A, right, which is the exponential regression. For your x value, that was hours. For your y value, that was bacteria. You hit OK, and you get this kind of thing again, right? Y equals A times B to the x power. You plug in for A, you plug in for B, right? Here's a correlation coefficient, same kind of deal, right? But if you want the equation, you just plug in A and B into that equation. That little caret, that's an exponent symbol. So if you plug in, you're going to get the same equation here. All right, so I'm going to head back to my iPad. And let's write this equation down. So using these data, write the exponential regression equation. We did an exponential regression, and we got y equals 17024 point, rounding all values to the nearest hundredth. All right. Don't worry about the rounding here. They only give us up to 0.4, all right? So just go to 0.4 times to the nearest hundredth, so times 0.25. I round that 4 up to a 5 to the x power. All right. So according to your regression equation, by what percent is the number of spores decreasing by each hour? All right, guys. I know most of you are going to say 25%, because that number there is 0.25. But if you remember from our exponential functions, right? Again, it's 1 plus or minus r, this number here, if we want to find the rate. So y equals a times that to the x, right? That r that is the percent growth or decay. So in this case, I know it's decay because it's less than 1, right? But we need to think, how much less than 1 is it, right? To get 0.25 inside this parentheses here, right, doesn't that come from 1 minus 0.75? So it's really a 75% decrease, right? A 75% decrease. Right? The other way to think about it, if you remember, right, each time we're multiplying by 0.25. In other words, we have 25% of what we have after each hour. So if we have 25% of what we had before, we're losing 75%. It's a 75% decrease. And how much bacteria would we have after 1 hour? So that data is missing here, right? But now that we have this equation, right, we could use this equation to predict how much we would have after 1 hour. So I'm going to copy and paste this equation. And all we got to do is plug in a 1 for x, right? Because x was the number of hours. And calculating this, we are going to get about 4256. This is 0.1, but let's just round. So about 4,256 bacteria. All right, I'm going to quickly go back to the calculator screen, just because I want to show you on that curve our estimation. All right, so after 1 hour, oh, why is this scale so weird? 1 hour is going to be here. Right, after 1 hour, right, using the equation, we said about 4,256, right? Wouldn't you agree that is about where 4,256 would be on the y-axis? So all we did is we just plugged into the equation, and we're going to get the same y value as it's going to be on this curve. So that is doing an other kind of regression. So it's exactly the same as doing a linear regression. It's just instead of getting a linear equation, well, what we get is a different kind of equation. So pretty much the only other type of regression we're going to be doing most often is exponential regression, which is why our warm-up was what it was, right? So hopefully you remember some of this, right, of our exponential functions, because we do need to notice percent increase and decrease stuff, all right? So number 2 here. About a year ago, Joey watched an online video of a band and noticed that it had been viewed 843 times. 1 month later, Joey noticed that the band's video had that many views. Joey made a table to keep track of the cumulative or the total number of views the video was getting online. All right, so letter A, let's make a scatter plot in our calculator. So let me head back to the calculator one more time. All right, let's make a new document. Don't save. Listen spreadsheet. All right, so over here we have months, and over here we have views. So let's type in our data. 0 months we had 843 views. 1 month we have 1355. All right, so 2 months we don't know the number of views. So don't even type this into your calculator, because if you leave this blank, your calculator is going to give you an error. All right, so don't even type in 2. Just go straight to 3 months. Right, in 3 months we got, or this person got 3430 views. After 4 months, 5856. After 5 months, 8721. And after 6 months, 13585. All right, so typing that data. Pause the video, take your time, type it in, make sure you're following. All right, and make a scatter plot of this data in your calculator. So let's add a page, data and stats, right, to see our scatter plot. Down here, this was months. Over here, this was views. And I see a bend to this curve, right? So it looks to me like an exponential regression, right? A linear doesn't look like it actually gets through most of the points. I think an exponential is going to fit this a lot better. So for letter A on the notes right now, I'm writing it looks like it's an exponential regression, or exponential curve is going to fit this data better. All right, so write a regression equation that best models these data. Round all values to the nearest hundredth. All right, so let's go to menu, analyze, regression. And again, we're going to go down to choice 8, which is show exponential. And wow, you see how nice that fits all the data? So letter B, write your regression equation. I'm writing y equals 853.26, right? 2 decimal places running to the nearest hundredth, times, in parentheses, 1.59 to the x power. All right, justify your choice of regression equation. I guess we did that in letter A just because it looks exponential, right? It was not perfectly straight. There was a curve to it, so it looked like the exponential would be better. All right, so I'm actually going to head back to iPad now. Change screens. Got a mirror every time. All right, here we are. Resume. So identify and interpret the ratio in the context of this problem. All right, this number here, that's called the ratio. Right, so the ratio shows it is exponential growth. And we gotta say more than that. Actually, don't even write this. What does that 1.59 indicate, right? Well, we know it's growing, it's increasing, but it's increasing how fast, by what %, right? So remember, it's 1 plus r, plus or minus. In this case, it's plus r, right? How much are we adding to that 1? We're adding 0.59 or 59%. So this is a 59% growth. And what is it? In views, right? Each month, right? So in a complete sentence, Joey is getting about 59% more views each month. All right, try not to say, or just don't say it's a 59% growth, right? We gotta answer in context of this problem, right? In context of this problem, so make sure you're mentioning views, you're mentioning months, right? You're mentioning these variables, right? That's really all you gotta do when it says in context. Just mention whatever the variables are. So Joey is getting about 59% more views each month. As shown in the table, Joey forgot to record the number of views after the second month. Use the equation from part B to estimate the number of full views of the all-in video that Joey forgot to record. So how many views did he get after 2 months? We got our equation. We can use this equation to fill that data in, right? So all we have to do is plug in a 2 for x, right? Because x was the months, right? X, y. And now we're solving for y, which is the number of views. So in the second month, he got, well, let me just type this into the calculator real quick. 853.26 times 1.59 to the second power. Hit enter. He got about 2,157 views. All right. So that's going to be it for other kinds of regression. All right. If your data looks like this, do an exponential regression. If your data looks like this, do an exponential regression. Right? If your data ever looks like this, right? We didn't do it today, but there's an option. It just says instead of exponential or linear, it's going to say a quadratic regression. Just hit that option, right? But of course, if it looks linear, do a linear regression. So now we have all these different kinds of regressions we can perform, right? Nothing is different except the type of equation you're getting. So that is going to be it for today. So quick lesson, but hopefully makes sense. Let me know if you have any questions. All right, as always, stay safe and take care. I'll see you guys on Monday. Yeah, so have a good weekend. That's right. Happy Friday. See you guys.